increasing cubic has this shape, decreasing cubic, something like this. All right, and pretty much at this point, all the rest of the power functions have shapes like the cubic one or the square one, with some slight subtle differences. The steepness and sort of the overall, sort of curves involved in those higher power functions sort of just cause the graph to get narrower and narrower as the powers increase. Okay? So if we have a graph like y equals ax to the 2k, and again here, k a positive integer, then this graph is going to look a lot like that quadratic graph. The only difference is sort of how steep the graph gets as we move away from the origin. So every even-powered power function more or less has this picture for its graph. If a is negative, obviously it's flipped over and it opens down, but more or less this is what every even-powered power function looks like. In a similar way, if we look at odd-powered power functions, y equals ax to 2k plus 1, what we get is, again, sort of that chair-style shape. We get something that looks more or less like this. This again, when when a is positive, opening the opposite way when a is negative. All right, now, why do we care about power functions? Well, power functions can be used to create polynomials. Polynomials are some pretty friendly functions. They have lots of nice properties. As we change the values of pieces that make up our polynomials, our graphs start taking on different and different shapes. Okay? The book talks a little bit about sort of the general shapes that you can get from polynomials with specific powers. I defer to the book for you to read that information. Basically stuff that you should have seen in a pre-calculus class, or something that you would have saw in your high school algebra class or another calculus class before this. Okay? But polynomials are some of the nicest functions we deal with in here. Nice thing about polynomials is that their range and domain are pretty easy to identify. Polynomials, you can put any value you want into a polynomial. Polynomials are functions that have domain in the entire real numbers. Their range obviously depends upon the power that you're working with, but you can sort of identify that without too much difficulty. All right, and that brings us to the end of section 1.1. All right, move into 1.2. Hold your applause. All right, so section 1.2. This section deals with combining functions, talking a little bit about some of the algebra that we can do with functions. And a lot of really basic and straightforward stuff. We can talk about combining functions into new functions. Some of the basics that we can do with functions, if f and g are functions. So f of x and g of x are functions. Then what we can do is we can add functions. Quantity f plus g of x is simply what we get when we add the functions f of x and g of x together. Nothing too strange about that, right? Pretty basic stuff. functions, well, we can subtract the 2. So plus or minus on those, pretty standard. We can also multiply functions together. We can talk about the product of f and g. The product of f and g is just the product of their individual values. The third thing we can do is we can look at the quotient of two functions, f divided by g of x. Again, that's just dividing the two functions. Let me check. The book talks a little bit about what the domains of these functions are. The domain of these functions is really just a matter of looking at the function and identifying, okay, what can I do with this function? What am I allowed to plug in to this thing on the end here? Okay. Look at some simple examples of these things. First example, suppose we're looking at 6x squared plus the square root of x. Okay. If this is our f plus g of x, what values am I allowed to use in this function? What can I plug into 6x squared plus the square root of x? What we can do here is we look at each piece and we say, okay, here's this power function 6x squared. There's no rules that limit what I can plug into this. But when I come over here and look at my square root of x part, I have to say, okay, square root of x, well, I can't take square roots of negative numbers. So I need to make sure that whatever I use here has to work inside the square root of x. And so here, our domain is a non-negative real number. 0 to 3. All right? Using those same ones, if we go down to, well, actually, let's do something a little different than that. Let's take a look at, oh, I don't know, 5x times 1 over x squared. Okay, this is our f times g of x in this case. What am I allowed to use here? Okay. Again, we look at each individual piece of our product if we have to, and we identify what can we plug in. 5x. I can put anything I want into 5x. Any real number works there. But this 1 over x squared part, I need to be careful of. There's values that I can't plug into the denominator because I'd end up dividing by 0. And so here, our domain must be everything except 0. Using our interval notation, this is what the domain there looks like. Alright? And finally, if we do one more, the third one. X minus 2 over x plus 1 squared. Here's our x divided by g. Okay. If we look at this one, if we look at the pieces individually, then what are we allowed to plug into the 6x minus 2? Sure, we can plug anything we want into 6x minus 2. In a similar way, if we ignore that this is a fraction for a moment, what can I plug into x plus 1? I can plug anything I want into x plus 1. Now, okay, each individual piece, there's no restrictions if I just focus on the individual pieces. But I have to remember, now I'm dividing. I'm dividing things. And so that introduces a new rule that I have to be careful of. Okay? As this is, I can plug anything I want into the top function, anything I want into the bottom function. But since this is a function on the bottom, I now have to be careful of what? I have to be careful about dividing by 0 here. I cannot divide by 0. So what values has that limited my domain to be? I can put in anything I want except for -1.